All right, section 2.7, derivatives and rates of change. Now, sections 2.7 and 2.8 are very similar in the topic that they're going to be discussing. We're going to get into this idea now of what a derivative is. The difference being section 2.7 approaches it more from focusing on a specific point on a graph, whereas 2.8 gets us into the more general application of the derivative across an entire function. Right? So you're going to see some pretty similar notations, terminologies, similar types of problems in these couple of sections. Right? So just keep that in mind. So 2.7 kind of gets us into the idea of what the derivative is, and then 2.8 gives us a broader application of it. Right? So they're very similar in the types of problems that we're going to look at to some degree. All right, so 2.7, derivatives, rates of change. Right, so we've mentioned the derivative before, right, at least the term. So what exactly is a derivative? Well, when we're finding the slope of that tan line, right, or the velocity of an object, both of these require the same type of limit called the derivative, right? So all that limit stuff that we did back in the first section, and when we talked about the secant lines and how the slope of the secant line can be used to approximate the slope of the tan line, right? That's ultimately what we're calling the derivative, that slope of the tan line. So our tangent definition, we've got that the tangent line to the curve y equal f of x at the point P, coordinates a, f of a, is the line through that point P whose slope is given by the limit as x approaches a of f of x minus f of a over x minus a. So whatever all that means. Well, let's go back to that kind of idea again that we were talking about in the early part of this chapter. All right, so if I look at the secant line, all right, the blue line that I have. Now I'm focusing on this point AF of A. So this is our point of interest. And I'm looking for the slope of the tan line at that point, right, whose x coordinate is A, so its y coordinate is f of A, right, A, f of A. And so we want the slope of the tan line, which is our green line, at that point. So what we did was we looked at the secant line, and we said, okay, let's just pick a second point on our line, give it coordinates x, f of x, so whatever x you choose, the function value is f of x. And I always worry about the basic algebra notation to all of this stuff. So now I'm looking at these 2 points on the secant line, and then we said what happens is as we take this x and move it closer to A, or as this point gets closer and closer to this point, if we travel along the curve, then the slope of the secant line gets closer and closer to the slope of that tan line. Right? So that was the approach that we took. And so in 2.1, and so what we did was we took these values of x that got closer and closer to A, right, from both sides, the left and the right. That's where we made those table of values, and then we looked at the calculating the slope of the secant line, and then we used our observation about the slope of the secant line to give us an approximation, or at least give us an idea of what the slope of the tan line would be. Right? So this is getting now more into the formal definition of exactly what that is. So when you talk about the slope of the secant line, remember that's the line with 2 points, a f of a and x f of x. So the slope of the secant line is simply change in y over change in x along that secant line. So f of x minus f of a over x minus a. And then for the slope of the tan line, that's where that limiting value came in. So if I look at the limit of the slope of the secant line as x approaches a, so the limit as x approaches a of f of x minus f of a over x minus a. So in other words, the slope of the tan line, maybe write it this way, is equal to the limit as x approaches a of the slope of the secant line. Right? So, but again, this is nothing more than what we did back in the beginning section 2.1, and we talked about the idea of a limit, right? And we did it in the context of tangents and using slope of the secant line to give us the slope of a tangent. So that's all this is, same thing. So from there, now we have kind of a formula that we can work with. So let's say, for example, take the function y equals x cubed. Let's find the equation of the tangent line at the point 2,8 on the graph of that curve y equals x cubed. Now notice, at the point 2,8, that's our point of interest, So the x-coordinate of that point is our a value. So our function f of x is x cubed. Our a value is the x-coordinate of that point of interest. So a equals 2. And then f of a, of course, would be the y-coordinate of that point, which is f of 2, or 8 in this case. So there's all of our notation. So first, let's find the slope. If I want to write the equation of a line, right, I need the slope of the line. So we did this back again in the earlier sections. Find the slope. So now we're finding the slope by defining that limit definition, the limit as x approaches a, of f of x minus f of a over x minus a. And so all I did was plug all of that into our limit definition. F of x is x cubed minus f of a is 8 over x minus a, which was 2. Now after that, once you plug everything into that limit definition, now you're just back to evaluating the limit, right, just as we did previously. So, and again, we're not using tables of values here, because notice in each of these cases, you're going to have a function that's undefined for that particular a value, because every time you're forming that denominator by using x minus a. And so, of course, if you just plug a into it, you're always going to get 0 there. So this gets us back into that idea of once we plug everything in and we want to evaluate the limit, we're going to have to find methods of rewriting that expression or that function so that we can actually then use direct substitution and plug 2 into this thing. So things like factoring, rationalizing numerators, simplification, that type of thing. So like we have in this case, and I also want to, notice with this one, maybe a reminder from algebra. You don't see this done very often, so I wanted to mention this because, it does come up in a couple of problems. Factoring sum and difference of cubes. Maybe a quick reminder on that, because, again, it comes up in a couple of different problems, so I wanted to remind you how to do that. So if you were factoring, and that's what we're doing in this case, we're factoring the difference of 2 cubes. We have x cubed minus 8. So when you factor cubes, they will always factor into a binomial and a trinomial. If I had the sum of cubes, it would be a plus b times a squared minus ab plus b squared. So this is just a little quick review on that, because again, it comes up in a couple of problems. So sum and difference of cubes. Difference of cubes, which is what we have in this example. I take the difference of the two things being cubed, a and b, times this trinomial, which is the square of the first plus the product plus the square of the second. And you notice in the second one with the sum of cubes, it's just a reversal of these. So the sign that you have here is always the same as this one, and this sign is always opposite. Right? But again, that's an algebra review, just to remind you, factoring cubes. Otherwise, again, basic process. Right? So once I have this factored, in this case, I could then divide out the x minus 2, and I'm left with the limit as x approaches 2 of x squared plus 2x plus 4, which we can use direct substitution, and I get m equals 12. Right? So again, there's nothing different here than we've already done. Once you set up the limit, then you're just evaluating the limit. Now, all of that is necessary to get our slope. Now, don't forget we were asked to write the equation of the line, the tangent line. So once we have the slope of the tangent line, then we're back to our basic, y minus y1 equals m times x minus x1. All right. And then we're plugging in x and y, the coordinates of our point to 8, and then the slope that we found, and we're solving it for y. So that would be our equation of the tan line. All right, now, we can use this idea generally now to say that the slope of the tan line to the curve at a point is the slope of the curve at that point. It's kind of the description that we used previously, so we're making it a little more formal now. So whatever the rate of change is, whatever the slope of the tangent line is at a specific point, can be used to give us the slope of the curve or the rate of change of the curve at that point. And that's ultimately the idea with the derivative we said. We're interested in finding the rate of change or the slope of a curve at a point. Now, there's another expression that can be used for the slope of that tan line. So if we take that definition that we just used, that limit as x approaches a of f of x minus f of a over x minus a, and we're going to replace x minus a with h. So in other words, whatever that distance is between x and a, we're just calling that distance h. And then if you take that equation and rewrite it, solving it for x, you have x equals h plus a, or x equals a plus h. And then we're just going to take that and substitute into our previous limit definition. In place of x, I'm plugging in a plus h. So instead of f of x, I've got f of a plus h. I still have f of a, so f of x plus a plus h minus f of a. Now, in place of x again here, where we're putting in a plus h, notice what happens if we do that. So I have a plus h, there's the x, and then we still have this minus a. But notice these are going to subtract out, and all we're left with is h. So f of a plus h minus f of a over h. That is the slope of the tan line. So it's two different definitions. So now you have two different ways that you can calculate the slope of the tan line. Now this, you notice in this one though, I almost forgot to mention this. Here we have x approaching a, right? And so we were calling that distance between x and a h. Well, as x gets closer to a, what happens to the distance between x and a? Well, it gets smaller and smaller and smaller. So as x approaches a, that would mean equivalently that h approaches 0. Okay, so be careful with these two different notations. H is the distance between x and a. So as x gets closer to a, then the distance between the two approaches 0. Okay? All right, so that's limit as h approaches 0 of f of a plus h minus f of a over h. So we've got now two different definitions that you can use to calculate the limit. I prefer the second one, the one that we just came up with, just because I find that that tends to be the easier one to work with in most cases in terms of simplification. Now, you could use either one of these definitions, does not matter. And when you look at problems in the solutions manual, sometimes they use this one, sometimes they use this one, and there's no reason for it. It's just that in some cases they choose to use one, in some cases they choose to use the other. I will always use the one that I have circled. I will always use that limit as h approaches 0 definition. I prefer that one, and again, I find that it's just usually easier to simplify that one in most cases. So that's the one I use. But there's nothing wrong with the other one if you prefer to use it. Feel free. So for example then, finding the equation of the tan line, same question as with the previous example. This time my equation is y equals 3 over x at the point 3, 1, so our a value is 3. And we're going to use our limit definition to find the slope. And be aware of that question, because once we get done with all this limit definition stuff, we're going to get into chapter 3, where we start looking at the shorter processes, quicker ways for finding these derivatives. If you're asked to find the slope of the tangent using the limit definition, then this is what you're going to have to go through. Right? And I will give you one or two of these on your next test where you're going to have to use this limit definition, so you need to know it. All right, so use the limit definition to find our slope. So first, I'm going to use this h definition. So we've got that limit as h approaches 0. This is the slope of our tan line, is f of a plus h minus f of a over h. And then we're just plugging in our a value, which is 3. So I've got the limit as h approaches 0 of f of 3 plus h minus f of 3 over h. Now from here, I'm plugging that into our function. Remember your basic algebra, folks. I see so many mistakes made right here with this definition. This is nothing more than evaluating the function f by plugging in 3 plus h. So our function f, which is the y equals 3 over x up here, here's our function. I'm plugging in 3 plus h in place of x. So I've got 3 over 3 plus h. Now f of 3, well, that's the y value of that point. That's our function value when x equals 3, which is right there. That's our y value. Right? If you don't believe me, plug 3 into the function. You've got 3 over 3. Well, there's 1. So this is nothing more than the y coordinate. That's f of a. So I got 3 over 3 plus h minus 1 over h. Now, like we said before, once you plug everything in, it's now a matter of simplifying this expression. Because notice again, just like with the previous definition, because of this h approaching 0, and the denominator is always going to be h, that's always going to be 0. Right? So you're always going to have to do some rewriting. You're always going to have to do some simplification with these. So here's where we're going to employ all those little techniques and tricks that we used previously to rewrite these expressions. So that's going to be your process with these. Now here's one that we didn't talk about before. We talked about, using conjugates and that kind of thing. Here's one with fractions in it. We call this a complex fraction because you have these smaller, or in this case, one smaller fraction within the big fraction. So that's called a complex fraction. There's a couple of ways that you can simplify complex fractions. This is the way that I typically prefer to do it. I find the LCD of the smaller fractions within the big fraction. In this case, there's only one denominator. It's 3 plus h. So I will multiply the numerator and denominator of the big fraction by that LCD, which again is just 3 plus h in this case. If there were multiple fractions, you would have to go through, find the LCD, and that's what you would use. All right, but again, this is a basic algebra technique for simplifying complex fractions. The other way to do it would be to add, or in this case, subtract the numerator, 3 over 3 plus h minus 1, put that in terms of a single fraction, and then divide by h, or multiply times 1 over h. But I tend to prefer to do it this way, and this is the way I always do it. So I'm multiplying then everything by 3 plus h. So if you distribute the 3 plus h in the numerator, 3 over 3 plus h times 3 plus h leaves us with 3. 3 plus h will divide out. That's the whole reason we multiply by that denominator. And then I've got minus 1 times 3 plus h, which is 3 plus h. Now be careful here, another basic algebra issue, and I see so many mistakes made. There's a subtraction sitting right here. So when I multiply 1 times 3 plus h, make sure I then distribute that negative through the 3 plus h. All right, so that's the reason for my parentheses here, because of that subtraction that's in front of that product. A lot of times I see that ignored or left off, and then you end up with signs being off and the simplification doesn't work out the way that it should. Every single one of these, I don't care which definition you're using. We talked about this back in 2.2, I think it was, or 2.3, whichever section. I keep forgetting that we did all the simplification. But the whole idea behind the simplification and the rewriting of the function is so that eventually, whatever that denominator was that was causing the problem initially, right? I can't use direct substitution here because of the h cannot be equal to 0. At some point, that has to eliminate itself from the denominator. It has to go away so that I can then use direct substitution. So once you, or whatever process you use to simplify these expressions, if it does not simplify in that numerator to where that denominator of h divides out, then something's wrong. That has to happen. Otherwise, you will not be able to use direct substitution, because as long as there's a factor of h in that denominator, I can't plug 0 into that denominator. So it's kind of a built-in check, at least, to help make sure things are going the right way. So if it doesn't work out, don't force it. I mean, you can't just make things magically appear that aren't there. So if it doesn't work out to where the h divides out of that denominator, then you've done something wrong. So now I'm going to distribute the negative. So I've got 3 minus 3 minus h. Okay, so that'll knock out the 3. That's 0. And now I'm left with this negative 1h over h. So there I can divide out the h in this case. And that's what we said had to happen. So that then leaves me with negative 1 over 3 plus h, which I can then use direct substitution, and I've got negative 1 over 3 plus 0, or negative 1/3. Now again, a reminder about your notation here. Notice that again, in each step of the process, I kept that limit statement. Limit as h approaches 0, limit as h approaches 0, and I worked on simplifying the fraction in each step of the process until I get to the point to where I actually plug in 0. Then I got rid of the limit statement, because now I'm actually evaluating the limit. Okay? So the notation needs to be correct. If you leave that limit statement off, I will deduct. And again, there is no limit statement on the final step because you're actually evaluating the limit. And I've got a value of -1/3. Now again, all of that's the bulk of the work. That's our slope of the tangent line, right? That's what we were finding. And now once we have the slope of the tangent line, then we're back to plug into the point slope form of our equation. So there's our y minus the y coordinate equals m times x minus the x coordinate. And then we just solve that for y. And again, that's basic algebra. I trust you can do that. If not, we're in really, really deep trouble. In the context of velocity, right? So all of that was talking about the slope of the tangent line. But remember when we talked about secants and tangents before, we did it in terms of using the secant to find the slope of a tangent line. We also talked about velocity. Remember we talked about average velocity and instantaneous velocity. So there's a lot of applications with the derivative in terms of velocity, because velocity is the rate of change in position. Anytime you're talking about rate of change, all right, that's what a derivative is. So if we're changing our position, the rate of change in our position is our velocity. And then for the derivative, it's the instantaneous velocity. It's just like you're looking at the slope of the tan line at a specific point on your curve. You're looking at the velocity at a specific point in time, the instantaneous velocity. What is the rate of change in position at that point? So notation, terminology a little bit. For position functions, it's tradition to use the letter S. For position, obviously S represents position. But then again, the notation, and it's all relevant to the function. I mean, you don't have to use S. You can use our function f. Typically, our variable when we're dealing with velocity is t, because t represents time. Right? Yeah, I mean, that's with any function, and you can use different variables and there, but it's tradition. S is our position function, so S of t with respect to time. And in this case, we're looking at f of a with respect to a specific t value, which we're calling our a value. Right? So don't get too caught up in the notation. That's just basic algebra. Right? We can call our function whatever we want to call it. We can use whatever variable to represent our independent variable. It's just tradition with velocity and position to use s and t. So we call this our position function. Now again, let's be clear on what we mean by position. S is the displacement, right? Or what we also call the directed distance of the object from the origin at time t. Or when we say origin, whatever our point of reference is. So in other words, because you can talk about displacement or distance two different ways. Let's say I'm going from point A to point B. Right, there's a lot of ways that I can get from point A to point B. I can do that. And I moved from point A to point B. That's displacement. That's that straight line distance between the location of our object at point A and the location of our object at point B. I could also go from point A to point B by doing this, right? And traveling over some scenic route, if you wish. Well, that's not displacement, that would be distance. So the distance traveled along this curve versus the displacement from point A to point B. Those are two different things. Now, of course, they could be the same if the distance traveled was straight along that horizontal line that I have drawn. Okay, so be clear on that. Don't misinterpret. Like I said, you got to be very careful about the language. Or half the battle with a lot of this is language, terminology, notation. So when we say position function, we're talking about, if I look at position A and position B, and I calculate the difference between those two, that's the displacement of my object, not the distance traveled. We'll talk more about that later as we get into application type stuff, right? But I want to be clear on the language here. All right, so we're using S for position. We actually do use V for velocity. So when we talk about our rate of change in the position function, that's your velocity. So call it velocity function V, or V of t, velocity at time t. or velocity at time a in this case where we plug in a specific a value. But since that is the rate of change in your position, then there's our slope of the tan line with respect to our position function, right? So if you want, we could call that S for position. So S is a S of A plus H minus S of A over H. What is our change in position over time? Remember, that's how we defined velocity early on. It's change in position over time. So what is your position at time A plus H? What is your position at time A? What's the difference? And then what is the change in time, which is our H value. Okay. So again, whether you use S, whether you use F, that's all arbitrary in terms of notation. Just be clear as far as what your function represents. That's always the bottom line there. But that's nothing more than the slope of the tan line. That's our velocity. So, for example, right, again, very much similar to the types of problems we've already seen, just in that context. So here we've got a rock thrown upwards on Mars with a velocity of 10 meters per second. Its height in meters after t seconds is given by that function h equal 10t minus 1.86 t squared. So that's f of t, or s of t if you wish. That's our position function, which in this case, position means height, right? Height in meters after t seconds. So call it s, call it f. It's our position function. It's the height of our rock. So question part A, find the velocity after 1 second. So we're looking for a v of 1. And what is the velocity after 1 second? That's v of 1. Here's our velocity function. V of t is the limit as h approaches 0 of f of t plus h minus f of t over h, or f of a plus h minus f of a over h. So in this case, since I'm looking at the velocity at 1 second, or v of 1, there's our a value. So I'm just going to plug that into our definition. So our f of a plus h becomes f of 1 plus h minus f of a, which is f of 1, all over h. Now f of 1 in this case, if you plug 1 into that function, there's our function h, or f of t up here. We plug 1 into this thing, you're going to get 8.14. So that's our function value at that point. Now from here, it's just basic algebra. So now we're going to plug in to our function. We plug 1 plus h into our function f, so 10 times 1 plus h minus 1.86 times 1.h, or 1 plus h squared. There's our f of 1 plus h, minus f of 1, which we already said is 8.14. That's nothing more than 1 plugged into our function, all over h. And now we're just simplifying, right? Now again, a lot of algebra mistakes. I keep telling y'all, I see more mistakes here with just the algebra. It's not the calculus. This is nothing more than a limit definition of the derivative. It's an expression that we're simplifying, but the most common mistakes I see made are just basic algebra mistakes. So that's the kind of stuff you're going to have to clean up and be careful of, because all I'm doing from this point forward is I'm simplifying that numerator. So I distributed the 10 plus 10h. Now the second part of this, if you take 1 plus h and square it, let me remind you of this because I see this all the time. If you have a binomial that you are squaring, remember there's a formula for that. This means 1 plus h times 1 plus h, because I'm not going to do this every time. And if you use your FOIL method, you get 1 plus 2h plus h squared, right? In general, if you take the square of a binomial, you square the first term, plus or minus, whatever's right there, twice their product, so 2 times a times b, plus the square of the second, right? That's the formula for squaring a binomial, or you do that, and you do the FOIL method. But too many mistakes I see made there, right? So a plus b squared is not a squared plus b squared. Get over that. Okay, so make sure that gets multiplied out, because obviously here you're going to see these pop up quite a bit. So that's basic algebra mistakes, and I see that mistake all the time. So clean that up, get over it. You shouldn't be making that mistake anymore. So what I did then to get the next piece of this was I did the 1 plus h, and then I also distributed that 1.86. Right? So the 1.86, once you multiply this out, 1 plus 2h plus h squared, then you distribute the 1.86, and I've got that. And then minus the 8.14. And then all of that is over h. So then we combined a couple of like terms up there, and I'm left with 6.28h minus 1.86h squared all over h. And again, notice I'm carrying my limit definition, my limit statement every time. Limit as h approaches 0. Until I get this thing completely simplified. Now notice in the next step, I can factor out, let me write this step out because I'm going to be clear here. I mean, you can, and notice I'm consolidating some steps. You're perfectly welcome to do that. Just make sure you're keeping things straight. Watch your calculations. Because what I did next was in this numerator is I just factored out the h, which left us with 6.28 minus 1.86h. And so now you can divide out the h in the numerator with the h in the denominator. Okay. I should have included that step because remember, that's our whole purpose. At some point, I have to get rid of that h in the denominator. And then that leaves us with 6.28 minus 1.86h, which I can now plug in h equal to 0. Here's our direct substitution, and there's our final value. Now, there are units on this because this is an application involving velocity. So velocity is always change in position over change in time. In this case, meters per second, right? So height in meters after t seconds. So our velocity is changing meters per second. Don't forget your units. I will dock you a point if you leave units off where they're applicable. I'm a stickler for units. Question part B. Same basic question. Find the velocity when t equals a, right? So instead of just a specific point, and this kind of makes more sense. I mean, why would I keep plugging in individual values for t if I was interested in coming up with a way to calculate that velocity regardless of what the value of t is? Then let's do it in a more general sense, do it in a more generic sense. So let's just find the velocity when t equals a. All right, remember this, when I said at the beginning of this section, there's kind of the specific application at points versus the more broad or general application over an entire function. And this is kind of getting into that idea. So find the velocity when t equals a. So I'm just changing my notation here. I'm going to let v of a, then our velocity at a, be the limit as h approaches 0, f of a plus h minus f of a over h. That's our basic definition. So what is f of a plus h? Again, I'm just plugging a plus h into that function earlier, 10t minus 1.86t squared. So here's f of a plus h, 10 times a plus h minus 1.86 times a plus h squared. All right, that's back into that original function h, minus f of a. Now in this case, I'm plugging a into that function. So 10a minus 1.86 a squared. Now again, the parentheses, because of the subtraction, I need to distribute the negative. Limit statement is there every single step of the way until I actually plug in my h. So I've got limit as h approaches 0. From here, I'm just simplifying, same as with the previous. So I've got the distribution 10a plus 10h. I've got the squaring of the a plus h and distribution of the 1.86. And then we've got the distribution of the negative of that, and the distribution of the negative. I had to cram it up here, ran out of room. And then we combine like terms. And notice every single one of those terms has an h in it. So again, you can factor that h out. Let me go ahead and I'm going to write the appropriate statement here. Now again, if you can bypass this statement, that's fine. I mean, like I said, you don't have to write every little nitpicking step, but at least need to see how you're getting from point A to point B. You know, how are you getting from the initial statement, which I absolutely should see, this, to the final result. All right, and if you consolidate a couple of those steps along the way, that's fine. So I'm factoring out the h, which leaves me with 10 minus 3.72a minus 1.86h. All right. And all of that is over h, and so we can divide out the h. And we said that has to happen. If that doesn't happen when I finish simplifying, then something is wrong. So that's how we got to this next statement. That's the limit as h approaches 0, etc. But now I can plug in h equals 0. And so then once I plug in h equals 0, notice I drop the limit statement. I've got 10 minus 3.72a minus 1.86. Do this. And as soon as I plug in 0 in place of h, now I can get rid of the limit statement. All right. And now that's 0, so that's gone, and I'm left with 10 minus 3.72a. Now, what that gives me is, there's a formula that I can use then to calculate the velocity for any given value of a. All right, so that's our velocity function at time t equals a. Now, notice again, I included the meters per second. I'm not going to get so sticky with that. I mean, if you actually plug in a value for a and you come up with a number for your velocity, then absolutely I expect that you include appropriate units. But when you're just talking about the function, I mean, if you include it, great. If you forget, I'm not going to dock you for that. But it is traditionally more appropriate to include the units because, again, this is a specific application of that function. Question part C. When will the rock hit the ground? All right. So again, there's different questions involved here. They don't necessarily all involve calculus, all right, but we're just interested in answering questions about the situation. So when will the rock hit the ground? Remember, we threw the rock up. It's going to eventually have to come down, even though we're on Mars, where gravity is less than it is on Earth. There's still gravity there. So eventually it's going to come back down. But general application, when is the object going to hit the ground? Well, when its height is 0. Right? So the implication here is then it's going to hit the ground when the height is 0, when f of t equals 0. So all I did was I took our function and set it equal to 0. And now you've got an equation that you have to solve. If this one ends up being quadratic or polynomial in form, I can actually just solve that by factoring. So I just factored out the t, and then we set each factor equal to 0, which, notice I do get two answers to this thing. T equals 0. Well, that should make sense because, you know, this is presuming that the rock is being thrown from the ground. So at t equals 0, the rock's on the ground. So that should make sense. But the one we're interested in is the other one. All right, so at some point the rock's going to go up, it's going to come back down, it's going to hit the ground. When does that happen? That happens when t is approximately 5.4 seconds. Okay? But again, that's no more than just basic algebra, solving a polynomial or quadratic equation. In this case, set it equal to 0 because I want to know where the height is 0 when it hits the ground. And then we're solving the equation. Now, once I have my solution, t equals 5.4 seconds, so that's how long it takes the rock to hit the ground. Question part D, what is the velocity when the rock hits the ground? Right, so we found our velocity function previously, which was that 10 minus 3.72a, what we found on the previous page. And so now we're interested in the velocity at a specific point in time, right? What is the velocity when the rock hits the ground? And we just found that our t value there, or our a value, would be 5.4. Right, so I wrote it both ways. I plugged in the exact value. I also plugged in the approximate, and that's sufficient enough for applications. And then we just did the calculation. Now, notice what happens here. So I've got 10 minus 3.72 times 5.4. I end up with a value of approximately negative 10 meters per second. Remember, that's our velocity, right? At time t equal 5.4 seconds. The fact that it's negative, what does that mean? What does that tell me? right? So now we're introducing direction components into this stuff. Right, so it's not just sufficient to say that my velocity is 10 meters per second, right? The rock is on its way down when it hits the ground. So the fact that that's a negative velocity, it's giving me a direction component, right? The rock goes up, the rock comes down. So when our velocity is positive, right, the rock is moving up or going up. When our velocity is negative, the rock is falling. We're going to continue to carry that idea forward. So we're giving a little more context, right? So not just the numbers themselves, but what does that sign of that number tell me in the context of the situation? So velocity, you can think of positive velocity as going up or moving forward, maybe. Negative velocity means the object is falling or moving backward, that kind of idea. But there's a lot of application that we're going to do with that later. All right, so then the derivative, right? So this, what we're calling the limit definition of the derivative. And so these two different definitions that we use, we also now have a notation for our derivative. The derivative of a function f at a number a, denoted by f prime at a, or f prime of a, if you prefer. And f prime of a is then given by those limit definitions. So that limit as h approaches 0 of f of a plus h minus f of a over h. Or f prime of a could be given by the limit as x approaches a of f of x minus f of a over x minus a, which was the original definition. So like I told you, either one of these can be used when you're calculating a derivative. I prefer the first one, but if you want to use the second one, you're more than welcome to use it. That's fine. All right, but again, we're calling this now f prime of a. We've got notation. So this is called the limit definition of the derivative. So like I said earlier, if you're asked to find the derivative of a function or the derivative at a point using the limit definition, then you're using one of these two. So then the tangent line to the function y equals f of x at the point af of a is then the line through that point af of a whose slope is equal to f prime of a. Right? So the derivative of f at a. So that just ties together the whole, limit definition of the derivative, what we're calling it, the notation that we're using. Now we're saying the slope of the tan line would be the line through that point whose derivative is equal to, or slope is equal to f prime of a, which is the derivative of f at a. So it's just tying together everything we've been talking about. The slope of the tan line at a is the derivative of our function at a. Those are one and the same. So then another example, using the limit definition of the derivative to find the slope, find the derivative, of the function f of x equals x squared minus 8x plus 9 at a. Right, so again, I just took now f prime of a, so we're using our proper notation now. We want the derivative of our function at a. And so you always want to make sure you're labeling exactly what it is that you're finding, because as you will see going forward in different situations, we're going to be working with multiple functions. Maybe I'm going to work with the function, maybe I'm going to work with its derivative, different variables, different values. So you always want to label exactly what it is that you have found or are finding. So this is f prime of a, and then there's our limit definition. So again, I use the h approaches 0, f of a plus h minus f of a over h. So I just plugged in again a plus h into our function, a plus h squared minus 8 times a plus h plus 9, minus f of a, plugged a into my function. Now again, parentheses, make sure you distribute the negative, all over h. After that, again, it's simplification. So there's the a plus h squared, minus 8a minus 8h, distribution of the negative 8, and then the distribution of the negative through that last piece, minus a squared plus 8a minus 9. And you combine a bunch of like terms there, notice, and what should happen, as we said, I should be left with nothing but terms that contain an h, so that again, you could then factor that h out of each of those terms, divide it out with the h in the denominator, and I'm left with 2a plus h minus 8. And again, that limit as h approaches 0 comes along every single step of the way until we get to the final step where now we can plug in h equals 0 into this function once we get rid of that denominator, which then turns this into 0, and I'm left with 2a minus 8. So that is our derivative. Let me go ahead and call it what it is. This is f prime of a. Okay? So then I'm asked to find the slope of that function at a couple of different points, 5, -6, 0, 9, 4, -7. So my purpose here is just, again, watch your language, terminology, and your notation. If I want the slope of f at each of those points, what is the slope of the function? It's the derivative. So if I want the slope of f at the point 5, -6, then I'm looking at f prime of 5. Then I'm just plugging 5 into that derivative that we just found. That's why I said be careful which function you're plugging it in. If I want f prime of 5, make sure I plug 5 into f prime. If I want f of 5, make sure I plug 5 into the original function f. Just be careful. At the point 0, 9, plug in 0. I want the slope of the curve at that point. So again, I'm plugging in 0 in place of a. In our derivative, f prime of 0, I get -8. And at the point 4, -7, f prime of 4, you end up with 0. Notice 2 times 4 is 8, minus 8 is 0. All right? So again, once you find the derivative, that's just a matter of plugging in the different values for x or a into your function. Question part B, find the equation of the tan line at each of those 2 points, 0, 9, and 4, -7. Again, that's nothing different than we've already done. That's taking our point with our slope that we find. So we found at 0, 9, the slope was -8 up here. And then we're just plugging that into our point slope form, right? So our y minus y1 equals m times x minus x1, solve it for y, and there's the equation of our tan line, right? Nothing different than what we've done before. I did want to mention the second one, though, because finding the equation of the tan line, rather, at the point 4, -7, just to remind you, notice what we found at f prime of 4 was 0. So the slope of the tan line there is 0. What does that mean? That means that it is a horizontal line. Remember, horizontal lines have a slope of 0. And so what is its equation? Well, you could go through all of this if you want to get that equation. Or, remember, if you have a horizontal line, the equation of a horizontal line is always y equals a constant. Well, in this case, it would be y equals -7 because I know that that line passes through the point 4, -7. So it's simply y equal to the y coordinate of that point. So just a reminder, because that's actually something we're going to deal with quite a bit in the context of some applications and observations. Horizontal tan lines, they play a big role in terms of giving us information about our function or function behavior, or in the context of application. All right, so where do I have a horizontal tan line? Wherever my derivative is 0. Okay, we're going to talk a lot about that. And then the equation of a horizontal line is y equal that y coordinate, or that constant. Okay, that is that section. That is 2.7.